All right, guys. So in the second part of 4.3, in which our kind of primary goals were to look at the relationships between the graphs of the first derivative, the second derivative, in comparison to what the function originally was itself. We're going to look into a term called concavity. All right. And concavity kind of leads us into our goal for this video, is to use the second derivative to determine the concavity of a function itself, okay? So let's think here for a sec what it actually means to have concavity, or to be what you see on the screen, concave up or concave down. Now, the simplistic approach to it is simply, does the graph look like it's upside down U, or does it look like it's a right side up U? That's the easiest way to kind of look into concavity. Now, the specific definition has a lot more to do with, what we've been talking about with derivatives. And so, let's say, for instance, if you see that the curve is below any of the possible tangent lines that could be happening through this interval of the function. As you can see here, the curve is below all of those tangents. That represents concave down. Now, on the other side of things, you can see that the curve is above any of some random tangent lines that are in the interval in this case, okay? And so this would be considered concave up, all right? This is showing that y prime is decreasing when it is concave down. So y prime decreasing when it is concave down, and then y prime is increasing when it is concave up. All right? And so kind of looking into it specifically, we use what is called the concavity test to determine when it is concave up or concave down. And so the concave test, all right, and this is all in regards to our second derivative. Our second derivative is going to help us find specifically where it is concave up and concave down. So here is our test that we are really looking at. We can say that if it is twice differentiable, so this test, let's assume that the function can be taken the second derivative of. We consider it to be concave up, where the second derivative is positive, okay? The second derivative is going to be positive, and then we say it's going to be concave down, where the second derivative is going to be negative, okay? So if the second derivative on any specific interval, all right, is positive, then it is concave up. And if it is negative, it's going to be considered concave down. So I think the kind of easiest part to look at some specific things is just to take a look at an example as to where it's going to lead us into. So let's use the concavity test to determine the concavity of a specific function itself. Excuse me. So let's think here for a sec. Let's say I have the function y equals x squared. We'll keep it really simple. And we want to know the concavity on the interval from 3 to 10. All right? On the interval from 3 to 10. Well, since the concavity test is all about the second derivative, let's find out what y double prime is. Well, y prime is going to be 2x, and so y double prime is going to be 2. All right, let me put that over here. Y prime is 2x, and then y double prime is going to equal 2. So let's think about what's happening at y double prime equaling 2. Well, if y double prime equals 2, it's always going to be positive because y double prime equaling 2 is a positive value. So the graph of y equals x squared upon any interval that is between 3 and 10 is going to be specifically concave up because it is always positive, okay? So if y double prime equals 2, this is always positive, right? Thus making the function always concave up. And it makes sense. Think about what y equals x squared is. It is our basic parabola function. You can kind of see that everywhere you look, let's say I have a tangent line, let's say I have a tangent line here, or a tangent line here, or a tangent line here, or a tangent line here. Wherever there happens to be a tangent line on this graph, it is always going to be below the curve or concave up. All right.